Tonight is today's date is the 11th of May, 2026. The time now is 9:40 a.m. 9:40 p.m. So I'm trying to model this properly. What do I mean? What do I mean? I have a cup here. I have a cup here. This is a cup I got. This cup is a model. It's a cup. It's a standard cup, and topologically, it's topologically, it has some dimension. So the principle we're gonna understand. How do I put it? So the principle we're gonna understand. This cup topologically has the same mesh as a torus, a donut. The same shape as a donut. Is it a donut or torus? A torus. So this cup here is equivalent to a torus. No matter how much I squeeze this torus, it's a torus by design. This cup here is a torus. This green cup I'm holding up in front of you is a torus. And why is it a torus? It's a torus because the geometry says so. Your geometry says so. The geometry says so. This cup is hard to work with automatically, but it's just harder to work with automatically. But if you know it's a torus, you can reduce it to a torus or kind of a regular shape of a torus. It's a single whole object. You're understanding that it's a torus, but the problem is this applies to geometry. So it applies to geometry. So applies to geometry. Applications of heterogeneous application of taking this cup that's green uh uh green cup and shaping it and reshaping it into a torus. I'm trying to have a holographic system for OBIX of Oscar, B for Bravo, I for Indigo, F for X-ray. So the optimized browser interface experience or Heart UI UX library. So this cup here is literally the pinnacle of my hypothesis. It's at the pinnacle. I'm trying to clearly demonstrate that this shapes here have some this geometry here is equivalent, one hole geometry because it has share one hole and a share one hole, and that one into the center. No, share two holes. Yeah, the share one hole here and one hole in the center. Ow, ow, ow! Let me get my hand out of the cup. No. So they share one hole because if you enter from one hole, it's not two holes. We have two sides to one hole, but the share two holes. One here and one in the cup here. So Troy system shares two holes. So the two holes when you flip it. So if you think of algorithms like backface curling, I'm gonna look at this from the geometry standpoint, not the projection standpoint. So the geometry basically not the camera standpoint, but the geometry standpoint. So this has two holes. No, this has one hole. How am I saying? It has one. It has one hole. No, two. Two holes, which it can be two holes, which it shares the same properties of the trucks. So depending on the two sides of think of it as I'm going to explain it very poorly, but basically I'm trying to rederive the concept. So give me some time. So how many holes is it? There's two holes. Why? There's two holes because there's one hole here, one hole here. No matter how you enter, one hole here, one hole here. So because you can see through it, but because it's so it has two holes. So one hole is a cup, and because it's it's not a torus. So that means it's not a torus. But you can reshape it. It's not a torus, but you can reshape it to a torus. But you can reshape it to a torus. Yes, it's just not the same thing, but you can reshape it to a torus. That must mean that it has the same problems. That are some problems. They can reduce to one whole torus. Because when you reshape this cup, when you I can't reshape this cup, but I don't know, but I don't have something that's hold. I'm trying to find that hold I can't find it now. So it has yes. So this is it. So this has one hole, one hole. I'm trying to think of what I don't say. One hole, one on this side, and one hole on this side. The two holes. So it has two holes. Yeah. So it has two holes. So it's the same thing mathematically. This is a tape. So it's two holes. So because it's both two. I'm saying this wrong. So what's my main points anyway? My main point is it has two holes, one, two for either side, but it is a closed hole. So it's a closed hole. So it's just that this isn't closed. So basically, it's a problem in geometry, and topology that you can reduce these two to one set of problems. And the problem is what I'm trying to use to render. When there's two holes, is a problem. It's a good problem, but here's one hole. One hole. So this has one hole. This has two holes, but they're the same because they have to share the same problem, and the same problem is used to reduce in geometry, two geometry problems. So it's a tomographic problem of geometry, and basically I was explaining that this hologram can be used to produce a hologram. So what do I mean by this? So this tape here, is is a simpler form to compute. It's not simpler. Is that the fact that this tape measure is more is computer is basically computer proof computer. Computer can work with this kind of shape here, this shape, because this shape here is simpler to do this shape here, this cup here, but they're the same shape, they're the same shape mathematically and geometrically. And by geometrically, I mean mathematically, geometrically, topographically. So this is this whole 3D system here hold here, and they share one, two holes, and they have one closed hole, one hole, one open hole, and because you can go through the hole and come out the other side, and go through the hole and come out the other side. But this one you can't. But this one's just they're the same shape, and because they're the same shape, they have the same principles to address here. So I'm trying to take this cup and project it as a torus on the other side of the screen. So so the share. So basically, if you have a camera and I'm trying to read this wireframe as wireframe and project it as a system of wire on the other end of the screen, obviously, digitize. I'm trying to digitize this cup. So have to identify all the properties of this torus. These are subgeometry. So these are substrate of the geometry that exists as a cup, and this cup will be what is here in the present. It's what I'm talking about. So so this is a torus. This is also a torus. But I'm trying to take this curve and shape it and render it on the other end as what's being projected at cup, and this digitally. So basically, doesn't matter the shape of this cup. This cup is easy to compute geometrically, and that's how some of the principles of the problem. So the principle is using geometry and tomography, topology, not tomography, not the area, topology, to create a wireframe that using like Z buffers, backface curling, which are standard methods. I'm trying to use backface curling, which is about the faces to model some regions that are the same, and use Z buffering to put those differences, 2D differences onto the screen as a 3D model. And that's the only thing I'm going to use. So the two I'm going to use are Z buffering and backface curling. So backface curling will do the same thing. So that's the two I'm going to need to do this. And I know that I'm going to do 3D, but the camera has to project it. And that's basically from this camera aperture. My mother's calling me. 1 second. So from this camera aperture. 1 second, guys. 1 second, guys. So this is the couple string, and it has the properties of a torus. So these are what I call a knot. So basically, it's not just a knot; it's basically a whole dimension. There's a lot of shapes like this. So remember, the two algorithms I did are Z buffering and backface curling to determine how this determine the holes topology of the shape. So we can have this a wireframe. So we can project the wireframe of this cup onto the computer, and that's the goal. If you can project this wireframe of the cup by taking the 3D by taking the two-dimensional picture of it in space and time, I've got a hologram that I can use to project again onto onto a surface. But you have to take a 3D model and digitize it. So, basically, if I can digitize this cup, with my OBIX library, O for Oscar, B for Bravo, Alpha Indigo, X for X-ray, which is an npm install O for Oscar, B for Bravo, Alpha Indigo, X for X-ray, OBIX, I can use it to determine how this cup how to use this cup, how this cup to project via backface curling and Z buffering based on the axis model, based on the plane axis. Okay, thank you for the video. So the first proof I'll try to demonstrate is the matrix model. Yes, I'm going to show you. I'm not. So this is the video here. I want to show you. It's a pen. So let me show you the pen. So this is the pen here. This is a pen here. So this geometry hemisphere. This hemisphere. So this is a wireframe, and this wireframe is basically a vector wireframe. See how it doesn't make it. Yeah, but move my mouse basically. Something my mouse. This one, you know. But it's slowing down here. It's not. Speeding up, slowing up, speeding up, slowing up. Yeah. So it's right to the mouse, but it has some. But this wireframe of net topology, this is net surface area, but it's just a wireframe of a subject of a. No. So basically, you go to take a 3D object of this. You go to have a hologram, take a 3D object, calculate the tomology algorithmically. So algorithmically, take the take a 3D projection through a 3D objects, determine the Z buffer. Not even determine, determine determine the backface curling. This is a subroutine, and projects determine tomography, determine the topology category based on backface curling and Z buffering. And then, this is a very vague thing I'm saying. It doesn't make any sense. Okay, because basically you're going to have the backface curling work on temporary subroutines, and you're going to have the Z buffer. So let me try to define the algorithm properly. Okay, so let me call two functions. Here, func buffer buffer z buffer z v is a type of vec3 and delta t d delta t buffer z. So buffer z will be position of zone. So to buffer z, you're gonna have to basically have the projection of the system onto the screen, onto the 2D canvas, and that will be a z-axis move. So basically, that's what buffer Z are going to do. So buffer Z will have this remove one dimension of the system and collapse into a two-dimensional shadow. So it will be a shadow that be a line going to a shadow, uh, of depth. So basically, it's gonna remove Z. So buffer Z remove Z. Uh, no, we'll store Z as a two-dimensional, two-dimensional. So basically, buffer Z. Let's vector delta T of time to buffer Z. So V dot A determinant 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 equals B squared minus 4AC. I would say that determinant equals 0. Basically, there are four algorithms I'm using. So the four I'm using is to determine the Z buffer, do the backwards curling, basically this is subroutine of the Z buffer, basically to identify subregions of the torus. And if this share the same properties of the torus, you have a holographic system. You have a hologram that's a torus that's equivalent to a cup. But that hologram of a cup is just arranged different. It's just arranged. So, it's just arranged differently. And that's all it is. It's arranged differently. And that's why I chose the cup. I chose the cup because it's arranged differently. So if you can just get a combination of the torus, you can have the shape of the cup based on the area or kind of the shape of the torus, which is this green cup I'm holding up. So thank you for watching, guys. Like, share, and subscribe. So if this is a torus, this is a cup. So just put it side by side. I don't think I'm doing this properly, but I'm doing this kind of my best ability because I can't really. It's late now. Thank you for watching this video. Okay, thank you for watching this video. I'll upload this now.